Engineering 305, example problem 5, chapter 5, number 8. We have a rigid plate C, which is used to transfer a 20 kip load. That is 20,000 pounds. That'd be 5 minivans. To a steel rod and an aluminum alloy pipe, as shown in figure 513. Here's the figure. So I've got a steel rod A on the top, and I've got an aluminum pipe down below that are supporting this 20,000 pound load, which is applied to the plate C in the middle, and that C is rigid. Ta-da! All right. There are no stresses in the rod or the pipe before the load P is applied. That is, they're not pushing on each other. The rigid plate doesn't weigh anything. It's a beautiful. So the only stresses we're worried about are from this 20,000 pound load. The cross-sectional area, so they've given us that. I should probably start scribbling this down behind the scenes. Maybe I'll pause and write it down. And then I've got the cross-sectional area of the rod and the pipe, which is nice. I don't even have to calculate it this time. Like last time I had to calculate it. Determine the stresses in the rod and the pipe. That's pretty much what we did last time. We had a rigid system that transmitted the load. All right, I'm going to pause. I'm going to write down this detail, and then we're going to jump in and solve stuff. So hold on. So I've got the key parts written down. I'll make that go away. And you can see I've got Young's modulus in the steel, the Young's modulus in aluminum, and then the area of the steel, the area of the aluminum. Find our stresses. Great. Okay. Start the same process. I'm trying to find the stresses. That's the force in the steel over the area of the steel. The aluminum is stresses in the aluminum equals the force in the aluminum over the area in the aluminum. Okay. I know that. So the steel, there's a load. If I draw that block, and they've already done that for us in. Oh, I can't do that. I grabbed the wrong thing here. They've already done a free body diagram. They're putting 10,000 pounds on either side, right? Because it was. Let's read their note. It was a 20,000 pound load. So they've already done that. They split that up, but essentially what you're getting is a free body diagram over here. I'm pushing down on this with 20,000 pounds, and my steel is pulling up. That's my force in my steel. Let me get rid of the picture. And the force in the aluminum is pushing up, right? So I get that equation out of this that if I did sum of the forces equal to 0, it would be the force in the steel plus the force in the aluminum minus 20,000 pounds, not 20 pounds. 20,000 pounds, 20 kips. But I'm just going to rewrite that. The force in the steel plus the force in the aluminum is equal to 20 kips. All right. So if I follow the same process, I've got, let's see, my unknowns are, I don't know this. I wasn't circling them before. I don't know my stress. I don't know my force. I don't know my stress. I don't know my force. If I talk about equations, I've got one equation. Here's two equations. Here's my third equation. And then I've got a fourth equation I can write down, which we know is the deflection in the steel is equal to the force in the steel, the length of the steel, the area of the steel, the Young's modulus for the steel. Write the same thing down for the aluminum. Force in the aluminum, length of the aluminum over the area of the aluminum, Young's modulus for the aluminum. All right. Wow. Okay, did I add more unknowns? Absolutely. I added delta, so this is 5, and this is 6. Didn't mean to circle them. But I did add equations 4 and 5. And if you remember example 7, okay, what do we know? Well, we need to know one more thing. And the thing that we knew was related to the deflection. We knew something that tied the deflections together. And in the last problem, we knew that the deflections were the same. In this problem, if we look back at the figure, when one deflects, when A deflects, that's how much B deflects. A gets longer and B gets shorter. And so we do know how this works. We do know how this works. That is, I'll say the deflection, we can do this, we can track our signs very carefully, or we could go a little slipshod. But I do know that delta in the steel is equal to the deflection of the aluminum. And I might choose to write this in absolute value so that now everything is positive. The reality is if I didn't do absolute value, I could track back and I could say, yeah, the one force is positive, one force is negative. I don't need to do that. What that would say is one force is negative. The force in the steel is positive. The force in the aluminum is negative. And that would make the deflection in the aluminum negative. And then the deflection of A plus the deflection B is 0. But this will work just the same. And this gives me equation 6 without any additional variables. And now I just plug in and solve the system again. It's actually going to be the very same process. I'm going to set, because I like kind of having that routine, I'm going to set my pen to black, not rainbow. I like the rainbow, but there's a place in it. This isn't it. Force in the steel, length of the steel, area of the steel, Young's modulus for the steel is equal to the force in the aluminum, the length of the aluminum, the area of the aluminum, and the Young's modulus of the aluminum. Now, in this one, I don't have that the length of the steel and the length of the aluminum are the same. That's okay. We just are going to punch in values, and we can rearrange this any way we want. I would start with saying force of the steel is equal to force of the aluminum times L over A E, and AE, area of the steel, E of the steel, over length of the steel. And just punch those numbers in, and we'll start getting out some values. So I got to go to the pictures because I didn't write down, I don't think I wrote down enough. I don't have the lengths. I do have the areas. But I don't have the lengths. Let's take a look a sec. Steel is 10 inches. The aluminum is 20 inches. So I'm going to write the force in the steel is equal to the force in the aluminum times length of the aluminum is 20 inches over the area of the aluminum was at 3. I got to slide it. Yep, 3 inches. And E for the aluminum is 10 MSI. Well, that's 10,000 KSI is the way that it's commonly expressed. The length, the area of the steel was a 0.08. I'm going to just pull it up here. No, 0.8 inches squared. 0.8 inches squared. Sorry, these are inches squared here. And then the length of the steel, E for the steel is 30 MSI. And I'm going to divide that by the length of the steel, which was 10 inches. Now, obviously, all the units canceled because this inch cancels with, well, I got to show you. This inch cancels with that inch. MSI cancels with that one. Inches squared cancels with that. So we just got to run the numbers. Hold on a sec. Let me do that. So that gave me that force of the steel is equal to all the way to the end here. FA, force of the aluminum, times 1.6. And then I've got to go back to the equation that's just showing up at the top of the screen force of the steel plus the force in the aluminum is equal to the force of the steel. Oh, sorry, I don't want the force in the steel. I want this to be 1.6 times the force in the aluminum when I substitute in, plus the force in the aluminum is equal to 20 kips. So 20 kips divided by 2.6. So now I've got the force in the aluminum is 7,692 pounds. And the force in the steel is 20,000 minus that. And I still haven't finished the problem. I have to go back and do the stress. Sorry. I have to do the stress in the aluminum is equal to 7,692 divided by the 3 inches. And that's going to give me a pounds per square inch. And that's, oh, I'm just telling you that's 2,500. I actually have the book sitting next to me, and they're telling me that's 25, which is approximately 2560 psi that they give me. And the force in the steel, stress in the steel, is equal to the 12,308, and I divide that by 0.8 inches squared, and I don't know the answer to that. Oh man, that's going to be 15,380 psi, but that comes from the book. I didn't actually turn the calculator on. And then the last thing they want us to do is find the deflection. And the deflection in the steel is going to be equal to the PL over AE, all values for the steel. So it's going to be 12,000, or sorry, and like last time, I'm going to make that sigma L over E. And so I'm going to do 15,380 psi times my length, which was 10 inches, divided by my Young's modulus, which is 30 MSI. And I'm going to calculate that out, and I am going to get, screen move, 0.00513 inches downward. Of course, that's the way I put my force on. My force is pulling it down. What did we have last problem? I think we had about 6,000ths of an inch, didn't we? And this time we get about 5,000ths of an inch. Now, this problem's a lot shorter. There's actually a lot more strain going on. That's okay. These deflections that we're talking about are very, very small, but we need to understand these deflections to figure out how the load gets shared. It's not, this typically is not the important part, but that's our avenue to say, okay, how much did our load get shared? And so there you go. I hope you can see the parallels between example problem 5.7 and this one. Honestly, I didn't expect it to follow exactly the same route, but I guess maybe I need to work another couple hundred of these. And let's continue to try to use that same strategy, because if we have a problem methodology that we can use and recycle and it's effective, that will make it an easier, hopefully an easier path to come up with solutions for the next one. So that path was, first we're going to write down what we're looking for, the stresses, and then we write the equation for the stresses. Then do we know something about the forces? Yep, they sum up to, because we know some force that was imposed on our system, so we know sum of the forces is equal to, and we can write a relationship that way. And then we know that certain parts of the model deflect like other parts of the model, and we can write our deflection equations and come up with one more equation there. So that's how our systems are now working out. Hope that helps. Take care.